this optimal receiver, and while writing, I made an error
Sir,
actually.
are you sharing your screen?
Oh, isn't it visible? It's visible. Yeah.
So can you reshare it?
Yeah, I will reshare it. And share, reshare.
Yes, sir, it's visible now.
Yes. Okay. So yesterday I made an error while writing. What I wrote was probability of correct detection given R. Right. This is what we wrote.
Sir, but you wrote that M hat was sent, so it meant the same actually.
Yeah, it meant the same. But what I missed yesterday was writing this R
So this R
on the
was
left hand.
there.
This R was
I
there.
Yes, sir. I wrote the notes today only after checking the video, so it was there.
Okay. Okay, this R was there. So then I don't know how I made this error because my notes are correct. I made an error copying from my notes anyway. Therefore,
Sir, but here you are writing correct detection, but yesterday you wrote correct decision. Or both are same or different?
yeah,
Like
both are the same.
okay.
Doesn't make a difference. Therefore,
Excuse me, sir.
yeah,
Sir, also you said you would clarify about that confusion like yesterday.
yeah. That's where I got confused. So actually, what I missed was, you are right, it is given R. I missed writing this, I missed copying this step, or rather in my notes, I missed this step. In the step was in my notes, I somehow got confused. Now this makes sense, I believe.
Yes, sir.
Yeah, Kirti, now is it okay? This is where we fumbled yesterday.
Yes, yeah, now it's fine.
Yeah, yeah. So I skipped this step, and while skipping this step, I made an error. So m hat equal to m. Fine. So now we want to design a detector that maximizes of correct detection or minimizes the right.
Sir,
Yeah.
we are having function as f of r vector, while integrating we are doing it with respect to dr. Okay.
Okay. And this integral you can have because it's cumbersome to write. You will have m such integrals or n such integrals actually, right? Because it's a length n vector. So it's an integral over n dimensions.
Sir, from last lecture onwards, you were using 1 cross m, then m vectors are now, and like.
So there are, let me clarify this. There are m possible symbols, n
Okay, sir.
okay. In case of
And
orthogonal signaling, m and n will be equal. Otherwise, the number of symbols will be more than the number of dimensions.
okay.
Fine. And
Sir, in
yeah,
this case, we are assuming same values of m and n, or
no, we are m and n are distinct.
okay.
Okay. In the last lecture, there was I said I defined G as this.
Yes, sir. There was some confusion from there on. I
Yeah. So
kept it.
n is the dimension.
Okay.
N is the dimension. So if you are talking about something like QAM, n will be 2.
Sir, and M is the cardinality of set S.
Yeah. M is the cardinality of set S.
Okay.
Okay. Fine. So this, and so now we want to maximize right. Make sense?
Yes, sir.
Now this is fine. Non-negative real number. So if then right.
Yes, sir.
So even
So
we could Like f of r also, it depends on f of r also, right? Why we are not taking that into
F of r is real positive for all, so probabilities are real non-negative numbers, right?
yeah.
So the sum of s- real non-negative numbers, or basically integration, is you are multiplying something with a real non-negative number and then integrating. So in order to maximize the integral, if you maximize it for each real non-negative number, then the overall integral will be maximized.
Yeah, okay.
Okay.
That's it.
Or we can say that m hat equals right. This is the posterior probability. Bayes theorem. Right.
Yeah, sir.
I will just try clean it up once.
Sir,
Yes, Shubhashi.
sir, but SM wasn't a vector, S was vector.
SMs were also vectors.
Okay,
SMs
okay,
are symbols, so they are vectors.
okay.
Fine. Since the denominator is independent of m hat equals right. Agreed.
Yes, sir.
Yeah. So what does this tell you? So what this tells you is, if you receive the vector r, then the symbol transmitted, or the estimate that maximizes the probability of correct detection is symbol that maximizes fine. Fine.
Sir, like,
Yeah.
can you state it slightly understand like why exactly it depends on a single symbol? It might depend on a single symbol.
No. So what you do is that so if you have the constellation, so what we do is we receive the sim or vector r, and we know the constellation S. We know the probability, or rather prior probability, of each symbol being sent. We know these things at the receiver. We
Yes,
have a
sir.
communication system set up. We note these things at the receiver. Then we also know right.
So we received R, like if we receive R and if we know S, like how will you calculate this exactly, sir?
Yeah, I'm telling you. I'm telling you. So see, we know that R is SM plus W, if I'm not wrong, or SM plus eta. This we know.
Yes, sir.
Yeah. So eta I know is sorry. This I know.
Yes, sir.
So R given SM sorry, comma. I know this.
So SM won't add any variance.
No. SM is a deterministic quantity.
Yes, 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 yes.
Given that SM, you can find the PDF of R given SM for each SM.
Yes, sir.
Fine. So we know the priorities symbol. We know R can yes.
Yes, sir.
So now let's write this down as an algorithm. So we receive Sn or we receive R, then step 1, calculate step 1.
Yes, sir.
Sir, but wouldn't F given R, R given Sm depend on eta, and eta is changing
So
every.
probably we see Adit, we cannot. So we do not. The problem that we have is that we do not know eta. We cannot know eta. We don't know noise. Noise is random.
Yes, sir.
So we don't know noise. So the task of detection is that given what information, whatever information you have, you want to uh, choose a symbol that maximizes the probability of correct decision. We have this is a so we know that there is a random noise. What we want is, given that random noise, we want to maximize the probability of detection.
Okay, sir.
Okay. So there is so once there is an additive noise, there is no going back to the noiseless case. Or information once lost cannot be recovered. So we have to try our best with partial information. And this is what we are doing. Choose m hat as the m that maximizes yeah. Yeah. So this algorithm is sensible.
Yeah, sir. Okay.
Fine. So now in the simple case, or in a simpler case, when PR or all the symbols are equally likely. Then fine. And this is the maximal likelihood or the ML receiver. Fine. This is, I believe, okay. This is the likelihood function. You have done the likelihood function earlier? Detection and estimation people?
Yes, sir.
No, this is the maximum likelihood receiver. Others who haven't taken the detection and estimation course can forget about this. This is the maximum likelihood receiver and kind of end of story, but we can make life simpler. How do we make life simpler? So we'll try to do that. So what we have is that m hat equals over m. Right? Now in the Gaussian case,
Sir, aren't we missing out the 1 by m term?
1 by capital M, how does that make a difference? That's a capital M.
Okay.
That won't make a difference. You want that I can solve the general case. Yes, you are right that I should solve the general case. Fine.
Yes, sir.
Case of Gaussian noise. Yes. In disappears. Fine. Last semester we derived the PDF of a complex Gaussian, or we looked at the PDF of a complex Gaussian that comes back to haunt us.
Yes, sir.
So now m hat equals x m.
Sir, this F R given SM for Gaussian noise is something that we have observed or is something that we have derived?
Uh, Mm, so it's an extension. So it's not totally observed. It's not totally derived. So we Gaussian distribution for a single random variable is observed
Yes, sir.
or is based on observe is an empirical kind of an expression.
Yes, sir.
Then when we extended it to two random variables, three random variables, conditioned on independence and all those things, we kind of derived it.
Yes, sir.
So it's not that it's observed, it's not it's derived, it's somewhere in the middle, or it's a logical extension of what has been, or it's kind of a logical extension of what has been observed. Makes sense, Adit?
Sir, R is Sm plus eta. I mean the
Yes,
vectorized version of eta,
yes,
right?
yes, yes. One upon n naught times. Fine. Now, uh, the log function is a monotonically increasing function. Log of x is monotonically increasing for x, or for non-negative x at least.
Yes, sir.
Fine. So since log of x is monotonically increasing for non-negative x, this equals m n log plus minus sorry minus 1 by n naught minus fine.
Sir,
Yeah. Yes, Adit. Adit. Maybe he got disconnected. So others fine.
Sir,
Yes.
sir, you're taking
Sorry.
so you're taking everything in log, right?
Yeah.
Okay.
Sir, is in there extra minus between 1 by n naught and the next term?
Yeah. This shouldn't be there. Yeah, this shouldn't be there. This is a product. Yes, this is a product of a log. Yeah, fine. Yeah. Now it's okay.
Yes.
Yeah.
So this will
So
be equal to log estimate, right?
log what? Uh,
Oh,
Log likelihood is a slightly different thing. That is a special case for BPSK like signals. That's a log likelihood ratio. Let's not go into that right now.
okay, sir.
Okay. So now the good thing is that this doesn't depend on m. This 1 over n naught doesn't depend on m. And let's write it as log of probability of Sm as xi m. We can do that. So
Yes, sir.
this is called xi. Xi and the capital xi looks like this. This is called zeta. Capital zeta is called and capital zeta looks like this. Fine. So, or uppercase zeta looks like this. So this equals this is minus fine.
Sir,
Yeah.
we are, so where is n naught part?
And not you can oh yes, and not will be required here.
Yes, because I, yeah, no.
Yes. And not will be required here. Or and not can absorb xim. Xim is a custom defined constant.
Yes, sir, then we need to make it that, we need to make that
Yeah.
Xim
So
by
xim,
n naught.
yeah, this is xim by n naught, and n naught gets absorbed into xim. Fine.
Yes, sir.
Yeah. So this is a good thing with custom defined constants. So the point, however, is that now for Pm equals 1 over m, or xim being of m. M hat.
Sir, Xim is probability SM, right?
N naught times log of probability Sm.
So, sir, how will it be independent of M if PM is equal to 1 by M?
Sorry, small m, independent of small m.
Okay, sir.
Okay.
Okay, sir.
That yeah, m hat equals m. Right?
Yes, sir.
What is this? What does this give you?
Some noise.
Huh? No. So given, so now given R, what Sm will you choose? I'll frame the question this way.
So it looks like this way. That is whatever as R we are like whatever R which is closer to which side of the SM, that we choose it as.
Yes. Yes. So we choose the Sm. Therefore, we choose.
So it becomes like a classification problem here then.
Yes, that's what I was saying, that this is where digital communication gives rise to machine learning. Or this is how the problems in digital communication led to what is present day machine learning. If you note that all the people working in machine learning, or some 20 to 30 years ago, or even 40 years ago, people who worked on communication problems were the first ones who started off all the machine learning algorithm part, not the computer science aspect of it. The all the pattern classification design, algorithm design, all that goes back to people who worked on both communication and signal processing, and that gave rise to the present day machine learning community. Therefore, we choose, or machine learning is statistics, which is also used in communication in the same way. We choose the SM that is closest to the received symbol, or SM that minimizes the distance, or that has the minimum, that has minimum distance from R. Fine.
Sir,
Yes, Adit.
sir, but wasn't this, I mean, without the mathematics also, wasn't it obvious that we should choose
Yeah.
the SM which is,
If this is not true, when you have non-zero, or when you have a dependence on xim, when you have a dependence on the prior probabilities, this is not true.
okay, sir.
See, we reduce this only when we reduce to this point only when we have a dependence on prior probability. Only when we say that the prior probabilities in all cases are equal. Also, sometimes, yes, Shubhashish, you are right. Also, sometimes there are things that are fairly obvious and yet you have to prove them mathematically.
Yes, sir.
So like 1 plus 1 equals to 2.
O- Over what field?
Real field.
Oh, okay. Yeah, I accept that in real field, but in binary field, I won't agree with you.
Yes, sir.
How do you define the operator plus?
That's one of the things we had to do.
Yeah. So, um, see, mathematics or abstract mathematics is hard, or abstract mathematics is like law. You don't know what. Has anyone read Feynman from my previous semester's recommendations?
Sir, I read QED.
QED is something totally different. I never understood that book. So because QED at times goes over your head, and because obviously it's hardcore physics. He tries to explain well, and Feynman is a good teacher, or was a good teacher. Anyway, so Feynman had this argument with a mathematician that you take something the size of an orange, you split it, and when you put it all back together, it's as big as the sun. And Feynman has this problem that he cannot. So for continuous functions or continuous things, that is okay. That if something is continuous, you can actually play around with the size, or you can play around with the scaling using some properties. But in Feynman's head, when you take something apart, like an orange, you can only go up to something as small as the atoms. or some fundamental particle. So you cannot get something the size of the sun from the size of an orange. So yeah,
Sir,
abstract mathematics that way is slightly hard. Yes.
no, sir. It's okay.
Yeah. So now based on this, can divide the n-dimensional complex space Cn into M such that if R is contained in Dm, then M. Right? You can do that. We can partition the
Yes, sir.
divide is not the right word here. Partition. So we can define a discriminant function, and therefore I can define this dm as the decision region for the decision region for the mth symbol as R such that I'll just make this bracket again. Yeah. Fine.
Sir,
Yeah.
MAT is the miss, right?
Uh,
Miss detection.
M prime. Yeah. M dash. No, this is
Yes.
we are not yet there. We are not yet in the case of misdetection or all, anything like that. We simply say that this DM is the region which is a subset of R or sorry R in Cn. Yeah. R in Cn such that probability of M given R is greater than probability of M dash given R for all M. For any other M, you the probability of having this thing is larger in this region. This is what we are saying here.
Okay, sir.
Okay. So we are not yet into the misdetection or wrong detection region. So machine learning people, you know the confusion matrix? Machine learning, anyone? The term confusion matrix, have you heard of it? Okay. Confusion matrix does not confuse people anymore. So, and this is called the map on the maximum I the decision region. Fine. This is called the map, and similarly you can have the ML decision region. So now who will ask the question that I'm waiting for? So if you look at this DM, there is something that this DM doesn't cover.
So boundary.
Yes, boundary. What do we do at the boundary? So if R lies on a boundary that is possible with probability 0, then we toss a coin. Simple.
Sir, can't we ask for a retransmission?
Yeah. So that is uh, algorithmic stuff. We can only at the receiver, we can only decide based on what we have. We can do that, obviously. There are codes, there are ways of doing that. Maybe when if there's a digital communication 2 course, I can possibly offer digital communication 2 as an elective. So if at all I offer digital communication 2 as an elective, maybe we can discuss this there.
Sir,
These
maybe
kind
a
of.
fourth-year course.
Sorry? Yeah, that's what
Maybe
I'm
a
saying,
fourth
that
year.
if I can offer digital communication 2 as an elective for for the 4th year, then this. But I somehow like teaching these 2 courses, principles of communication and digital communication in succession. I get to ruin your interest in my field that way. So now we have next thing, probability of error. So simply defined, probability of error is summation m goes from 1 to n m, or probability sm, whatever you like, right? Probability that the mth symbol was transmitted, and probability that the mth symbol was received in error. This will be the overall probability of error.
Yes, sir.
So now the question is, how do we calculate probability of error in the mth symbol? That can be done as that you transmit SM, but right?
Yes, sir.
Equals right?
Yes, sir.
Or the probability of error is the mth symbol landing into every other decision region other than the intended decision region. Okay. And therefore,
So that should be SM dash, right?
SM, no, given SM, you have transmitted SM, given that it lands into SM. So suppose I transmit this kind of QPSK, or this is called pi by 4 shifted QPSK 51T.
Okay, so the DM dash is the domain over all the symbols that are not M.
DM dash is
So
the decision region.
okay, sir.
Okay, so see, if you suppose you transmit the pi by 4 shifted QPSK, this is called pi by 4 shifted QPSK, and then you would the simplest thing to do would be that if it lies in the first, or according to what we have done till now, the decision regions, you can see that the 4 quadrants can act as decision regions.
Yes, sir.
In this case, simply based on what we have done till now, the 4 quadrants act as decision regions, right?
Yes, sir.
So now suppose you transmit this and the received symbol lands you over here, or suppose you transmit this, then if the received symbol lands in any of these 3 quadrants, you will have an error event.
Yes, sir.
Or you transmit this, not changing colors, then the error event will be these 3 quadrants, right?
Yeah. Yes, sir.
So makes sense now?
Yes, sir.
Yeah, so transmit something and then you define the error event, and this is how you calculate the probability of error. So this, I believe, is a good point to stop. We can pick up from here on Tuesday.
Yes, sir.
Any
Sir,
questions?
so the quiz will have up till the last lecture, right?
Quiz will mainly be based on constellations or constellation design only.
Okay.
Okay.
Okay, sir.
Yeah,
Sir,
and this subject, it's becoming harder because see, the kind of things that we are doing are not that easily extended to objective type questions.
yes, sir.
Yes, sir.
Yeah,
Sir, one doubt.
yeah.
Uh, in the first few lectures, you stated that from the transmitter, the same message is sent at least multiple times. Like, so when the
Next
receiver
chapter.
is
Next to next chapter. Next chapter is band limited channels. The chapter after that is error control coding.
okay,
Okay, that is a part of error control coding. So 2 chapters later.
okay, sir.
Okay. We'll stop here then.
Yes, sir.
Okay. Bye all. Have a nice day.
Bye, sir.
Thank you, sir. Bye.